It does. And it's raining. All right, so we're going to work through several fairly basic examples of L'Hopital's rule. And when I mean fairly basic, what I mean is your initial fraction, first of all, it is a fraction. And secondly, its initial setup is going to be L'Hopitalable. It's going to be 0 over 0 or infinity over infinity. So we have a request here for 18. I think this fits into the bill. So if you plug 0 in for x, what do we get in the denominator? 0. And if we plug 0 in for x in the numerator, we have e to the 0 is 1 minus 1 plus 0 is 1. So we have 0 over 0. So this says L'Hopital's rule applies in number 18 because if you try to plug 0 in for x, you get 0 over 0. And the fact that we're approaching 0 from the right specifically, at the moment, doesn't really change what we do. As with a one-sided limit, the thing to do is see, can I just do this the way I would do any old limit? And if I can, I don't need to worry about the fact that it's coming from one side. So at this point, because just plugging in 0 gives me 0 over 0, that means, okay, let's do L'Hopital's rule. Take the derivative of the top, take the derivative of the bottom, and see what happens when we try again. So when we take the derivative of the top, what happens to e to the x? E to the x. I'm just going to shift the negative here. What happens to the minus 1? 0. What happens to the minus 1x? Minus 1. What happens with the denominator? N times x to the n minus 1. If I try to take the limit now and just plug 0 in for x, what do I get in the numerator? 0, because 1 minus 1 is still 0. And what do I get in the denominator? Also 0. So, do L'Hopital's rule again. So you can do L'Hopital's rule multiple times if you're still getting 0 over 0 or infinity over infinity. So we'll have limit as x approaches 0 from the right still. And now what's the derivative of the numerator? E to the x. What's the derivative of your denominator now?
N times n minus 1 x to the n minus 2.
Yeah. And now, if you do this, we get what in the numerator?
1
Over
0.
still 0.
So that's fine.
Now we've used the fact that it is a one-sided limit, and we say, okay, and now we're reaching back in our memory to chapter 1 from last, March. If we ever get 1 divided by 0 as a limit, that indicates that we're approaching a vertical asymptote. And whenever we approach a vertical asymptote, the limit is some kind of infinity. So we got to decide, is it plus infinity or is it minus infinity? And because it's a one-sided limit, it's going to be one of these. If it were a regular limit, we could reasonably say it doesn't exist because it's going to be infinity or negative infinity. But because we're approaching a one-sided limit, we have to decide which is this. The one-sided limit implies we have to make a choice. So, as we approach 0 from the right, say 0.1, is e to the x going to be positive or negative? Positive. All right, so the numerator is going to be a positive value. We don't really care a particular value. We just care plus or minus because we just decide is it plus or minus infinity. And n, they told us n is a positive whole number. Integer, same thing. So positive whole number. So since n is a positive whole number, n times n minus 1 is positive. And x is positive or negative. Positive. And a positive raised to some power is positive. So the denominator is a positive times a positive times a positive. We call that positive. And therefore, this is heading to which infinity? Positive infinity. So that is how you would approach 18. You would L'Hopital it twice, try to take the limit directly. Oh, we got 1 over 0. Anytime it's not 0 over 0, that indicates a vertical asymptote, which in turn indicates an infinite limit. You just have to decide, is it a positive or a negative limit? We can only take this limit with any confidence from the right because we don't know what n is. In order to take the limit from the left and be able to decide one way or the other, we would need to know an actual value for n. Because that would then, like, this eventual exponent would kind of indicate where x to the n is positive or negative. Any follow-up on 18? All right. And then I guess we'll just progress backwards across the board from, I think, on the whole, more difficult to more easy. All right.
I'm gonna move backwards.
So we're going to work backwards across the
I'm
board.
just gonna start at like,
You know, that's stupid. Let's work from easy to hard.
wait, why not?
All right. Now, did we already do example 1 yesterday? Yeah? No? All right. Well, I can't remember either, so let's just do it. If we just take the limit directly,
Oh, you didn't finish it.
what do we get? 0 over 0. So what do?
Yeah.
Differentiate. And we just differentiate top and bottom separately. When we differentiate the top, what does e to the 2x become? 2e to the 2x. What does minus 1 become? Poof, it goes away. What does x become on the bottom? 1. So you don't really need it. And now you can try to take the limit again, and you have 2 times e to the 0, and that is 2. So in that version, 0 divided by 0 is 2.
That was like 2 degrees.
Over there in 18, 0 divided by 0 is positive. All right, so in limit land, if you get 0 over 0, it could be anything. You don't know what's going to happen until you investigate. All right, now, when you're approaching infinity, we got to kind of think about what does the graph look like? Where is it headed? Or just kind of think, as x gets really big, do these numbers get really big or do they approach some value? So the natural log of x graph, you should have a mental image of that. For natural log of x, where does it start? Like what x values are allowed to plug in? So can you do the natural log of 0? So you can start at 1. You can start with any positive, but you can't do 0. Natural log of 0 is undefined. So what you actually have on the natural log graph is a vertical asymptote at 0, and then it's coming up and doing one of these things. And so as your x's get bigger and bigger, what happens with the natural log of x? Where do they head? They head towards positive infinity. Now it looks like it's tailing off, but it's always heading up. It's always getting larger and larger. So this is going out towards infinity, but it's going there pretty slow. As x heads to infinity, what does x do? It goes to infinity. Which of these do you think gets towards infinity faster? Probably x, which means that the limit is not going to be infinity to the whole thing because the bottom is growing faster than the top. So if you drew y equals x, you'd have this thing. So you can see this is getting up higher faster than the other guy. And since that's the denominator, we can kind of think this infinity is bigger than the top infinity, if that makes any sense. Or at least you're heading there faster. So that means that we're probably going to get a limit, but to find out exactly what it is, we got to L'Hopital this. So we can L'Hopital this because this is an infinity over infinity situation. What's the derivative of natural log of x?
What was that?
So differentiate the top, we get 1 over x. Differentiate the bottom, we get 1. And then bop. So this is just limit as x approaches infinity of 1 over x. And now if you take the limit, what's 1 divided by infinity? Nope. 0. So this is, think about when we divide by infinity from a number. Remember my pizza analogy?
Oh yeah.
I go get a pizza and I cut it up infinitely many ways with all of my friends and everybody gets to sniff the pizza. Basically, if I shared the pizza with all 4,000 people in this building, everybody gets to lick it. So basically nobody gets anything. So if you have a solid real number and you divide that infinitely many ways, you're getting 0. Each slice is going to be 0 sized.
I don't want to.
So x heads out to infinity so much faster than ln of x that infinity divided by infinity here is 0. But that's not always the case. All right, here, x approaches infinity. And what's the numerator?
X squared.
X squared. If you do infinity squared, what do you get?
Oh, infinity.
Like super infinity. So it's infinity. In the denominator, it might be easier to think of e to the negative x as what?
E. 1 over e to the x.
Yeah, that might be easier to think of as 1 over e to the x. So instead of trying to think, what is e to the negative infinity? That's weird. Try to think of that as 1 over e to the x, and that way you'll at least get to deal with a positive exponent.
That's a beautiful.
That's ugly. Yes,
Why can't you mix it up?
you could bring it up. Why don't we? Because if we did e to the x times x squared, and we have x run to infinity, this is infinity, and this is infinity, and now we're really lost, because now we have infinity times infinity, and that's not L'Hopitalable. Suppose you could say that's super infinity. We'll get there. All right.
Infinity squared.
It'll be, well, I guess infinity cubed. So let's work through it another way,
Zero.
I guess. 1 over infinity in the denominator is
0.
0.
Zero. I was right.
You know what? I actually like your way better, Noel. All right. So you could look at this and say, why don't we just bring this upstairs? Yeah, you're right. Yeah, let's do that. So this is, you know, just because it's L'Hopitalable doesn't necessarily mean you do L'Hopital's rule.
What?
It might be better to rewrite it like this.
Limit to infinity.
Yeah, we're not doing L'Hopital's rule. This is, oh, it's a fraction. Let's do L'Hopital's rule. Oh, wait, we get infinity over 0? That's not like L'Hopitalable. So we rewrite it,
It's 2 infinity.
and this is infinity times infinity, and this is going to be infinity. That's like common sense. So yeah, no, you're absolutely right. That's the best way to do it.
Why did you say no to infinity times infinity first?
Because I wasn't thinking what,
Wants to be special.
because I wanted to be special, but I was stupid. I tried to be special and I wasn't. So you're right. Infinity times infinity is obviously infinity. So just do that. So just because you have a fraction does not mean, oh, I'm just going to L'Hopital this. This is not L'Hopitalable because it's not infinity over infinity or 0 over 0. But it's so much easier if you just say, let's just rewrite the thing so you don't have a negative exponent. And oh, that's like super easy. Sam, then Javier.
Limit as x.
You're going to say the same thing? Okay. What are you going to say?
So infinity divided by 0.
Yeah. Like when you have like 5 divided by 0 or 1 divided by 0, that indicates a vertical asymptote, which tells us we're heading towards infinity. Well, if that's true for like 1 divided by 0, it's even extra true for infinity divided by 0.
Okay. Back to what you said yesterday. You said infinity is not a number, so we can't think that way. That's why I asked.
Yeah.
And I talked to Snow
Yeah.
about it, and he said it's not a number either. So you're lying.
Yeah, but we can treat it as though it were a number sometimes.
Well, if that's the case,
Sometimes.
from the example
I'm
yesterday,
leaving myself an out with that sometimes.
from the example yesterday, why didn't we treat it as a number?
I can't remember the example
I don't
yesterday.
either.
Okay, well,
Wait, how does x approach infinity? How does when x approaches infinity?
No,
Yeah. So as x is heading towards infinity,
that's
e to the x is heading towards infinity, and x squared is also heading towards infinity. And they're multiplying. So if you have an infinitely large thing times another infinitely large thing, the whole item is going to be infinitely large.
What if I just put no?
I don't.
Would that
No, if we're going to have x approach infinity, then you have to make your piece with the limit being infinite. You can't use the does not exist out unless you have something like this, where it's a normal two-sided limit, and you're going in opposite directions from either side. But if we're dealing with x approaching infinity, then we've already kind of made our peace with infinity. There, that means we have to accept the possibility of it. This guy. Now, sometimes they're annoying and they say, hey, let's have x go to negative infinity. Bunch of jerks. Let's do that here too.
That equation.
It looks annoying. It's not that bad. So you have two ways to attack this. You can do this the pre-calculus way or the L'Hopital calculus way. Pre-calc way is actually pretty easy. On top, who's going to get towards infinity the fastest? X squared, right? And he gets there so much faster that we can say he dominates the other terms here. So the x squared grows so much faster than the x or the constant that it's really the only thing that matters as x goes to infinity. So you can say as x heads to plus or minus infinity, the only thing that matters in the numerator is 5x squared, because it's growing so much faster than the linear or the constant. Same thing in the denominator, the only thing that matters down there is 3x squared. And then you can say, hey, well, 5x squared over 3x squared, I can simplify that pretty easy. Bonk. Got 5/3. Done. Ta-da. So if you have like a regular rational function and x is heading towards infinity, you're basically just finding the horizontal asymptote. And the easiest way to do that then is say, you're the only thing that matters, you're the only thing that matters, reduce the fraction, see what you get.
But now I go back
Kind
to
of
plus
number
2.
is-
Whatever. But this is L'Hopitalable. Like if x heads to negative infinity, then this thing is going to plus infinity and beats everybody else. This thing goes to plus infinity and beats everybody else. So you have infinity over infinity. So you can do L'Hopital's rule. And if you did L'Hopital's rule, this becomes 10x minus 3 over 6x plus 8. And then you can try again, you'd have negative infinity over negative infinity, so you can do L'Hopital's rule a second time. If you did L'Hopital's rule a second time, derivative of top is 10, derivative of bottom is 6. And then that reduces to 5/3. So there's two ways to attack that sort of thing. You recall what you did. Any questions with this? You okay? Is that yours?
No.
Okay. No water. Passing this back and forth.
I don't know,
Goes back to the black. So. No.
What? Okay.
Usually, that's why I'm here. Any follow-up questions on this guy? And then we can use that same sort of idea on top of like one term beating up the other terms that are less powerful over here in this last example that I have. So as x is heading to negative infinity, where is x squared headed? Positive infinity. That beats up the 2. So the whole thing up here is heading towards plus infinity. And when you square root it, it's still going to be infinity. So we end up with infinity on top. On the bottom, this is heading towards negative infinity. So could we L'Hopital this? Yeah, we could. Because it's infinity over infinity, the signs don't matter. But we can pre-calc it because we know x squared beats up 2 when x is huge, right? X goes whole power with infinity beats up to 2. All right, so the only thing that really matters in the numerator is the square root of x squared. Now, you got to be careful with that. What's the absolute value? What's the square root of x squared? Absolute value of x. And as x is heading to negative infinity, the numerator is going to be positive, and the denominator is going to be negative, but otherwise they're the same because they're both just x, right? So this is going to be negative 1 because it's the same value. It's x divided by x, but one's plus and one's minus because of the absolute value. So you can say that's negative 1. Now, if that's like, what's going on? You can L'Hopital it because infinity over infinity. The only downside with L'Hopital is that you got to do a little bit of chaining. So if you do the derivative of the numerator, we get 2x times x squared minus 2 to the negative 1/2, and I forgot something, times a half, right? And it's all over 1. So we cancel out the 2's, and we have the limit as x approaches minus infinity of x over the square root of x squared minus 2. Oh. Learn your pre-calc methods
Isn't
too.
this the one
That's like the one that you showed me earlier, yeah. So you can L'Hopital this, but then it leads you to the same thing, just upside down. So
So
you
then,
really
L'Hopital that,
yeah. But if we L'Hopital this, where is it going to take us? Back to here. So that this is an infinite.
awesome.
This is an infinite loop. This is a vicious cycle of L'Hopital rule actually getting us nowhere. So that's why I'm showing you these kind of pre-calc methods of like, oh, this term dominates the other term, so it's the only thing that matters. And then you can take the square root of just the x squared and pretend the minus 2 doesn't exist. Because when we're out at infinity, honestly, what's another minus 2? Who cares? And so on. So watch out for those sorts of situations where L'Hopital's rule, yeah, technically it's allowed, but it doesn't accomplish anything. Try something different. We have a little bit more notes. So that, I think, covers our basis for like regular situations, where a regular situation is 0 over 0 or infinity over infinity, or a very easily simplified or manipulated fraction that gets us like something nice, or something that we can use pre-calc methods on. But then we have other situations that are not one of those, and that's going to take us back into notes land. So here are notes
No, I never
on,
remember.
because you didn't have me for pre-calc. So in pre-calc, that would have been when you were finding horizontal asymptotes of rational functions.
I think I remember that, but not.
Wrong set of notes. Here they are. All right, so there's a summary of L'Hopital's rule. All right, so there are other indeterminate forms. Indeterminate just means we don't know what it is. It could be anything. So like 0 over 0, we don't know what 0 over 0 is until we investigate further. 0 over 0 could be anything in limit land. Same thing with infinity over infinity. And here are other indeterminate forms that don't play nice with L'Hopital's rule unless we like do some pretty heavy algebraic manipulation of the function that we're dealing with. So if you see 0 times infinity, you don't know what that is. It could be 0, it could be infinity, it could be anything in between. And the way you deal with it in limit land is you got to manipulate the function and try to create it into a L'Hopital situation. Same sort of thing with 1 raised to the infinity. Like 1 to the anything is 1, except 1 to the infinity might not be 1. Also, 0 to the 0. 0 to any power is 0, but anything to the 0 power is 1. So 0 to the 0, which is it? Is it 0? Is it 1? Is it 12? I don't know. You got to investigate further. So 0 to the 0, 1 to the infinity, infinity to the 0, they're all weird situations. Again, infinity to the 0. Anything to the 0 power is 1, but infinity to anything is infinity. So who wins? Does infinity win or the 0 power win? Investigate further. And then infinity minus infinity, it could be 0, but it's not like 5 minus 5, it's definitely 0. Infinity minus infinity, you don't know what it is. So all of these are things that we can't figure out just from looking at them, but they're annoying because they don't play with L'Hopital's rule nice. So we need to then try to think of what to do with it. And then things that look weird, but we do know what they are things like infinity plus infinity, or negative infinity minus infinity, or 0 to the infinity, as opposed to infinity to 0, or 0 to the negative infinity. So if you see any of these, you should know, oh, I actually know what that is. I don't need to go any further. If you see one of these things, you say, I don't know what that is. Yeah, no. Because infinity to any power is infinity. But anything to this, yeah. So when we have these conflicting statements, Anything to the 0 is 1.
I agree.
But-
Except
0 to the anything is 0. So which is it?
one.
Which of those rules wins? When you have two rules that are like hard, fast, always rules that then come in conflict with each other, you can't apply either one of them, and you then have to go investigating and limiting. That's true. That's what's going on for all of these. Like anything minus itself is 0. But how fast you grow out towards infinity has an impact on what infinity minus infinity is going to be. 0 times anything is 0, but anything times infinity is infinite. So when you multiply 0 and infinity, who wins? They come in conflict. So all of these, you have hard, fast rules that are in conflict with each other in each case, and that's why we don't know what it is. Kayla.
Why is
That is a really good question. I don't know why 0 to the infinity is 0. I don't know why this is not one of our indeterminate forms. Maybe because if the base is 0, that's just what the base is. And you really do have nothing. Yeah, if you multiply nothing to itself infinitely many times, you're still going to have nothing.
But if you're multiplying infinity 0 to any number.
So a 0 power means you're dividing by itself. Yeah.
Yeah, so wouldn't it be the same infinity being divided by the same infinity? If that's the case.
Again, infinity is not really like a number. So you keep trying to make infinity into like a number, and infinity sometimes acts like a number, and sometimes doesn't, and acts more like a direction or a way out there thing. So we want to treat infinity like a number, but it's just not.
So it's a distance.
It's a distance that's like just so huge it can't really be measured.
You can't say it's a distance divided by the same distance.
Yeah. I think that's my best explanation. Like, anytime we're talking about infinities, I've thought a lot about infinity. I'm still talking over my head. So, like, I don't know if any human with a finite mind can really grasp infinity completely. Oh, you're saying these things?
Yeah.
Because a negative exponent means 1 over 0 to the infinity. And if 0 to the infinity is 0, then we have 1 over 0, and that's infinity per the vertical asymptote. So that, okay, now I got you. I thought you were pointing out what looks like a conflict between these things. All right, so things to watch out for. L'Hopital's rule can only work if you have 0 over 0 or infinity over infinity. So if you get one of these things, the goal is to manipulate the function into being some sort of fraction where you get something that you can use L'Hopital's rule on. And that leads us to our final set of notes here for the year. So here are general guidelines for using L'Hopital's rule. First, just try to take the limit directly, and if you get something nice, awesome, you're done. Try to take the limit directly, and if you get 0 over 0 or infinity over infinity, do L'Hopital's rule. And then try to take the limit again, and if you get something nice, you're done. If you get 0 times infinity, you can turn multiplication into division by like switching an exponent negative or something. So 0 times infinity is, oh, let's turn multiplication into division by throwing somebody down the stairs and then see if that gives us something that we can L'Hopital. So 0 times infinity is usually like the least bad non-L'Hopital scenario for us. Because it's not too hard to turn multiplication into division. If you do infinity minus infinity, that means you have multiple terms. Maybe you can combine them into a single item with a fraction somehow. So often you're going to have like one of those terms or both of those terms are fractions. Try to combine them together with like a common denominator or something, and then see if L'Hopital's rule works. And we'll see these examples tomorrow. The fourth situation is if you have like one of these exponential versions of something that we don't like. This is the worst scenario. This is you like take the natural log of the limit, and then you use the natural log to jump the exponent out and go from there. And it's a nightmare. So we'll definitely work through that, if not tomorrow, the next week. So we'll start looking through these different situations tomorrow when things are not just like directly L'Hopitalable. Like if you have x to the 5 times e to the negative x, and you're doing the limit as x approaches 0, then this is 0, and this is 1 over, not a good example. Then you have infinity times 0. Because you have infinity to the 5th power, and then 1 over infinity is 0. So what we would do is we would throw e to the x down the stairs and make the exponent opposite. Now it's division, and now you have some that you can do with L'Hopital. Now you have infinity over infinity, and you would just take the derivative like 5 times. You should always be able to do that. So again, we'll get into particular examples tomorrow for all of these situations. Or at least some of the situations, we'll get the others next week. I should return to the start of class tomorrow.